Thank you. So as I said before, we are part of GE Renewable Energy, and we are headquartered here in Kolding in Denmark. Our global manufacturing footprint includes production facilities in or close to our main markets, with 13 factories on 4 continents. In addition to that, we have technology hubs in Denmark, the Netherlands, India, the UK, and the US. As of January 2021, we employed a little bit more than 13,000 people worldwide, as I said in my introduction. Working closely with our customers, we design and supply rotor solutions for wind turbine projects across the world. Since 1978, where we started our adventures into the wind business, we have produced more than 241,000 blades, corresponding to approximately 121 gigawatt, and each year actually effective saving nature from more than 251 million tons of CO2 emission. About 1 in 5 turbines have LM WindPower blades. Let me see how I can shift this one. Great. Next slide. Technology is key for us. Through technology innovations, we have actually reduced cost of energy by 10% every decade for the past 3 decades, boosting annual energy production and efficiency. The rotor is the motor, as we say, and when we say technology, we mean size, materials, manufacturing, intelligence, and features to boost the annual energy production. The rotor blades only represent approximately 6 to 8% of the total lifetime cost of an offshore wind turbine. And the most direct way to decrease the cost of wind energy is by increasing the rotor performance, and thereby the annual energy production of the wind turbine. With 10% increase of the rotor diameter, you actually increase the annual energy production by 10% as well. Ever since we began producing rotor blades in 1978, blade has become longer and longer, as you can see on the picture here. And actually from the very start, people has asked, well, now the blades can't grow any longer, and the history has shown that that race continues with larger turbines and larger rotor diameters. I actually still do not dare to predict when this race of scale will end. Let's have a look into the design of a rotor blade. And that's quite an advanced process where highly sophisticated design tools are used to determine the aerodynamic performance and loads the blade must carry during its lifetime. The optimized structure of a wind turbine blade is a balance between many parameters like performance, loads, mass, and many other performance. A wind turbine blade is built like a composite beam structure. On the outer surface, we have the surface coating to protect the blade from wear and tear. And often the blade also has a separate leading edge protection layer, since the leading edge is the most exposed area to wear and tear. Then just after that, then we have the surface structure, which defines the aerodynamic shape of the blade. In general, the surface structure is built up as a sandwich structure with biaxial reinforcement layers and a sandwich core. The main load-carrying part of a blade are the spar caps, which consist of unidirectional layers of reinforcement in the blade length. The spar caps in the upper and lower shells of the structure are kept apart by a number of shear webs. Then we also have some metal parts. We have a lightning protection system that can either be a mesh, a copper mesh on the surface, on the outer part of the blade. It's not a solution that LM uses. We use a down conductor system as shown on the picture here. And then finally in the root end you will have either bolts or inserts as we use in order to attach the blades on the hub. What are the materials that are used for wind turbine blades? For the reinforcement, it's mainly glass. With the longer blades, we have seen a shift towards carbon fiber and especially glass hybrids because they provide an advantage of only have to use a small fraction of carbon fiber because that's quite an expensive fiber compared to glass. The polymer matrix are thermosets, resins, epoxy vinyl ester and polyester are the main resin types you will see in blades, and we use all of them. The sandwich core is balsa wood, PET, PVC has also been used in the older blade. Today it's mainly PET and balsa. The surface coating is either polyester or polyurethane. And then the metal part, as I described before, down conductor and inserts. If we look at the manufacturing process, it's a high level. It's 6 process steps with pre-molding, gel coating, where the molds are prepared for molding and the surface layer is applied into the mold. Then we have the dry layup, where all reinforcement, core material and other materials are applied into the mold. Then after that we go to the resin infusion. It should state resin infusion, where the dry layup is covered by a thin plastic foil and the resin is infused under vacuum. So the process that we apply is vacuum assisted resin transfer molding, VATM in short. Then after that we come to assembly. When the resin has been infused into the dry fabric and the laminate has been cured, then the vacuum foil is removed and the surface are prepared for gluing in the webs and defining and the assembly of all the parts. Then we have curing again, and then we come to demolding. The molded blade is released from the mold and then transported into the post-molding finishing area, where the final finish of the blade is performed and where 3 blades are matched into one set of more or less identical blades. So that's the build-up of a blade and the manufacturing process. As you've learned that I've been with LM for more than 30 years, so let me take you back in time, because that also shows where we are coming from. So when I started at LM, or let me take you all the way back to when we started going into to the blade business. Actually, it was a little bit by coincidence. Some people knocked on our door and asked if we couldn't produce blades, and we said yes to that. At that time, it was 5, 6, 7 meter long blades. Then when I joined 12 years after that in 1990, the main product was a 12 meter blade for 150 kilowatt wind turbine. The weight of the blade was 830 meter, and it had a bolt circle diameter of 600 millimeter, just so that you get an understanding of the size of the blade, the main product we had at that time. And actually the picture you see on the lower left there, that's such a 12 meter blade, so you can get an impression of the size. The manufacturing process at that time, that was wet hand layup, as you see in the upper left. And what you see on the picture is workers that are distributing the resin into the laminate and pressing entrapped air out of the laminate with rollers. The largest blade at that time was a 17 meter blade, just manufactured for prototype testing on a 450 kilowatt turbine. And as I said before, already with 17 meter, people were asking, well, there must be a limit to how long these blades can become. 2 years after I was employed in 1992, I became the project manager of the longest blade to be designed and manufactured at LM since the very start in 1978. It was a 24.0 blade, a 24 meter blade with a weight of 3.8 tons and a circle diameter of 1.4 meter. The prototype blades were manufactured and installed on a 1 megawatt demonstration turbine at a Danish utility in 1993. And with that blade, it was twice as long as the main product. We have the 12 meter and 7 meter longer than the longest blade we had in our blade program, the 17 meter. So it was really a challenge. We actually had to rethink the whole structural design and the manufacturing process. We had to develop some new manufacturing equipment in order to manufacture and handle such a large blade, and we really thought that was really a big blade at that time. The manufacturing process was still wet hand layup, but we started to see some of the limitations of this manufacturing process. There is some limitation of how much glass you can put into the mold before the resin start curing and so on, and you needed to break up the layup process a number of times in order to put in the full laminate. Further, as you can see here, it's an open mold process, so we actually also had a desire to improve the working environment and especially to reduce the styrene emission resulting from the use of polyester. Hence, we started to evaluate different alternative manufacturing processes and decided to develop the VATM, the vacuum-assisted resin transfer molding process, as the new manufacturing process to be applied for future large blades. The shift to the VATM process happened in the late 90s, where the blade length had reached approximately 30 meter and a weight of 5 tons. The picture you see in the middle, just after year 2000 here, is how the dry layup was performed in the early days. As you can see, the layout is highly manual with no automation at all, and it was still fairly possible to position the reinforcement in the mold without having to walk on the dry laminate in the mold. And many of the process steps like gel coating, post molding, finish were not changed at all. While the blade length continued to increase to new breaking world records, in 2004 we we designed and manufactured the 61.5 with a blade weight of 19 tons and a bolt circle diameter of 3.2 meter. Then the next record was broken in 2012 with the 73.5. Now the blade mass reached 26 tons, but actually the bolt circle diameter was still kept with 3.2 meter. Then 2016 we were all the way up to close to 19 with the 88.4. Now the blade mass was 34 tons and the bolt circle diameter 4.18 meter. And then 2019, the longest blade on the market, the 107 with 50 tons and bolt circle diameter of 5.4 meter. So we started in the late 90s with a blade mass that was like 5,000 or 5 tons, and now we are with the 107 we are at 50 tons, so a factor 10, 30 meter, and now we are more than 100 meter. But it's basically still the same manufacturing process. So we have had to develop that process, stretching it to accommodate the increasing blade length and blade masses. Deposition rates had also, of course, had to be increased significantly, both in laying up of the dry fabric and the resin infusion, in order to have a throughput, an acceptable throughput, and in order to optimize the key processes, we have introduced machines to assist the people. In the middle, you can see a dry fabric layup head that is on a gantry arrangement. And below that, you can also see a robot arm in the spraying of gel coat into the mold surface. So even though we have introduced several machines, blade manufacturing process is actually still quite manual and people dependent. And manufacturing control and training, that's still quite essential for us to produce blades. So let me give you a little bit of my outlook here to future manufacturing of wind turbine blades. If we look at the blade length, then that will still continue to increase, both for onshore and offshore. With the 107, the 100 meter mark has been passed, but already blades have been announced to be introduced into the market in the coming years that are longer than that for offshore. For onshore, the wind turbine blades also have increased dramatically in size, and we've passed the 80 meter mark, and we are heading towards the 90 meter mark. So that's how we see the challenge on the blade length. That will continue. Then there's been some suggestions to new ways of manufacture wind turbine blades, and there's been suggestions of modular wind turbine blades, and we've seen a few examples of such modular blades being tested. But so far, most blades are manufactured in a single piece setup, and I believe that will continue to be the case for offshore wind turbine blades, since the manufacturing plants are located directly at the seaside, so that the blade can easily be transported from planned to the offshore site by ship. For onshore wind turbine blades, transport of blades from plant to site is an increasing challenge, especially to location with complex accessibility. To overcome the logistic challenges, segmented blades have been introduced, and we have developed such a segmented blade concept, and actually with that, new opportunities for alternative manufacturing processes has been investigated, especially for the tip part, because that is now quite a smaller part, still in the size of 20 to 30 meter we envision, while the inner part still will be produced in the same state-of-the-art manner as we produced a single piece blade. Automation. I do believe that we will see a higher degree of automation in manufacture of wind turbine blades in the future, especially for the tip part of this segmented blade concepts. We are investigating additive manufacturing and the use of thermoplastic material. An introduction of thermoplastic material will also open up for new joining techniques like thermal welding, which again potentially will result in a higher degree of automation of our manufacturing process. Even though I believe that we will see a higher degree of automation in manufacturing of wind turbine blades, many manufacturing processes will still remain manual, and that's actually because that's the most cost-efficient way to perform these manufacturing process steps. Now I'll shift to talk about our sustainability efforts. And as I said in the beginning, sustainability and automation, in my view, that's both solutions to our overall objective to continue to be a profitable and green business, serving our customer with wind turbine blades. So it's a little bit of the same with different perspective. We are proud to be part of providing a green energy, but at the same time we also recognize that we are a manufacturing business, and we have a footprint, and that's why we in 2010 we started our sustainability journey by signing the UN Global Compact, committing to report on our sustainability performance. Probably very few people have read our reports, but the value of reporting comes from the rigor it gives in the understanding of our business and finding areas to improve. We like to say that sustainability is not about hugging pandas. Of course, we love pandas and we love the environment, but that's not what drives a long-term sustainability strategy in a business. We've been able to uncover many opportunities to link our business and sustainability goals, including operational improvements, serving our customers, reducing risk, motivating people, and much more. Reporting on our sustainability performance allowed us to learn more about our business and identifying opportunities to drive further sustainability improvements. As a responsible business in the green energy industry, we also want to be a leader and take concrete actions in the short term. That's why we in 2016 set up an ambitious pledge to become the first carbon neutral business, wind business by 2018. To go carbon neutral, we followed 4 main streams: accounting for our greenhouse emissions, reducing these emissions as much as possible with a focus on energy efficiency in the first years of the program, as this was our number one source of emission. Switching the remainder of our electricity to renewables. And finally, we balanced our remaining emissions by supporting verified carbon reduction projects in the countries where we operate. By following these steps, we were able to reach our goal, achieving carbon neutral status by August 2018 as the first business in the wind industry. And we have continued to maintain this carbon neutral status every year since then. While we are proud of this achievement, we also recognize that we are only one link of the value chain of a blade. We share our knowledge openly with all who are interested in starting the journey to go carbon neutral. We created an easy to follow 10-step guide, which you can find on our website if you are interested in that part. Carbon neutrality, that's all about balancing. On one side of the scale, we have the emission we create in our business, which we can reduce as much as possible each year, and then balance the rest by supporting carbon reduction projects. In the first year of our sustainability program, our electricity consumption accounted for 41% of our total emission. With focus on energy efficiency, we have been able to reduce the energy consumption and resulting contribution to our overall CO2 emissions significantly. So far, the carbon neutral program has delivered impressive cost savings on energy bill. And in 2019, electricity actually only represented 14% of our total emission. So it's down to fifth place if you look to the right. The next untapped opportunity is reducing the waste of materials and developing ways to recycle that waste. We are working on how to reduce the waste used in our products, for instance, by sourcing materials in the actual size we need. Currently, about 20% of the materials that goes into our factory actually goes directly to waste. So reducing the amount of manufacturing waste represents a huge opportunity to save on cost and CO2 emission. Further, we are working with our suppliers to be able to supply materials close to our manufacturing sites to reduce the CO2 emission from transport of materials from suppliers to our factories. Delivery of materials and waste disposal represented in 2019 combined more than 50% of our total CO2 emission in 2019. And that's even with the great achievement of $12 million in waste reduction savings. So a lot of cost to be saved, but still more potential. Over time, we have expanded our approach on sustainability beyond our own business. And today we are actually considering the full blade life cycle. You can think of the blade life cycle as beginning with materials which go into our manufacturing process and become a blade. Then the blade is then installed on a wind turbine, and it produces energy for around 25 years. Eventually the blade reaches the end of its life, and then we are very interested in what happens. Sometimes the blade can be reused, and actually there is a market for for second-hand sales of turbines, even after 25 years. We're also looking at extending the lifetime of turbines and the lifetime of our wind turbine blades. Then some example of repurpose has always been shown. The use of blades into bridges, sculptures, or playgrounds, and we love when we see that kind of examples. But mostly the blades are disposed when they reach of the end of life, and that can either be landfill or incineration, or it can be recycling, and we are working very hard with the industry to increase the recycling of end-of-life blades, so that we will see more of that. So for now, I say the way to dispose a blade is actually, as I said, that's mostly into landfill or recovery, like incineration, where you recover the energy by burning the blade or by recycling. We would like to work more on how the pyramid is shown in the left upper corner, to reuse or repurpose our blade or do more recycling of it in the far future or in the future. Let's have a look at our manufacturing process. So to reduce the carbon footprint from our blade, we have started with our area of influence, and that's from the moment where materials leave from our suppliers to the moment where our customer picks up the blades at our factory. The carbon neutral commitment has been a great driver for our operational efficiency, and that has led to significant cost and emission savings. But if you look at the total emission of CO2 from a wind turbine blade, then our area of influence actually only represents about 13% of the total emission. In fact, 76% of the CO2 emission occur in the supply chain from resource extraction. To put that into perspective, when the blades reach end of life and sent to landfill, then that actually only represent like 1% of the emission in the lifetime of the blade. One way to reduce the impact from materials is to use recycled materials instead of raw materials. And as an example, here we have switched to recycled PET instead of balsa wood or virgin PET as the core material in our blades. We're also working with our supply chain for them to use more recycled materials in the supply they give to us. But still, 20% of the materials supplied to our factories end up in waste. And out of that 20%, close to 50% is disposed by incineration, and only 25% is recycled. And we would actually like to see more of our waste being recycled than landfill or put into incineration. So we are also working with our supply chain to be part of that journey, and we are working with waste manager to increase that recycling part. As I said before, one avenue to deal with the CO2 emission and the waste part. That's to use materials that are easier to recycle, and such an example is the Zebra project. That's a French consortium with a goal to develop a zero waste blade and to reduce the carbon footprint in the lifetime of a blade. Here particularly we are looking at thermoplastic resins and how waste sorting and end-of-life handling can be done in a way so that the carbon footprint of a blade will be reduced significantly. I will close up with a summary here, some bullet points from our experience working with sustainability. So, going beyond carbon neutral, we need to work on sustainability across the whole value chain. And for us, sustainability is a mindset, and we have used lean as a strong foundation in our sustainability work. Waste reduction is our next opportunity in our sustainability journey. And as a responsible business, we need to drive that cultural change with a paradigm shift. So we as a company need to be part of it and not just look at our own area of influence. We need to look at both upstreams and downstream impact and work with that with our suppliers and the waste handler that handles end-of-life blades. That concludes my presentation here. Thank you very much.
Thank you very much, John. Thank you for an excellent presentation. We gave a very broad overview of both automation, well, the journey of the industry, automation, and then, of course, also the sustainability agenda. I assume that you're ready to take some questions, and I'm happy to report that we have a few. So let me start by David Hauber, who's got a question about the construction of the spar. So he asked, is the spar carbon fiber?
Yes, in some cases it is. It really depends on the customer and the design the customer desires. So if blade mass is key, then we can produce lighter blades by using carbon fiber. And yes, we have blades where the spar cap is carbon fiber. Majority of the blades has a glass fiber spar cap. The very long blades for offshore mainly has a hybrid, but we certainly also have full carbon blades.
Thank you, John. There's another question from Craig Pisbila. I hope I pronounced that correctly. And the question is there any relationship between length and number of bird strikes? So blade length, relationship between blade length and bird strikes.
Yeah, I'm not going to say, there's been many studies of say how a turbine is part of the environment and how birds adapt to the turbine, and actually my understanding they adapt quite good to it. They understand the turbine. Of course, on occasion we see bird strikes, but the studies I've seen, that's actually very rare. And I don't think that it's necessarily a question about blade length. Say if you look at the tip speed, then the turbines with different rotor diameter can have the same tip speed. So I think it's more about how fast is the blade turning, the tip speed, than blade length, I would assume.
Okay. I hope that clarified that question there. So let me just go to there's a question from Stephen Beecher. He starts by saying, impressive presentation, John. Great advancement by LM. Could you please provide an update on the progress of the Zebra project using the helium thermoplastic resin?
Yeah.
Have you reached the stage of comparing performance with a thermoset product?
First of all, the Zebra project has just been started. So we are setting up all the requirements for the testing and so on. We've done the first comparison. We produced a number of components with the helium resin. That's for sure. But in our evaluation of such a new resin, that takes years. So we take it from very small coupons and testing of that, looking at the performance, looking at how to manufacture laminates with the helium resin in the right way so that it provides the right performance. And we are just at the very start of that. The project started a couple of months ago, so we are just at the beginning.
Okay, thank you. Let me move on. There's a question from Sake Ivanov. He says also, thank you for a great presentation. And then he said, could you compare the cost of 8 1.5 megawatt wind turbines with the cost of one single 12 megawatt turbine?
I'm sorry, I can't do that. Well, first of all, because I don't know what the price of a wind turbine is. I'm not a turbine manufacturer, and also it's actually not just straightforward to compare cost of different products. It depends very much on what kind of materials you use. If you use more carbon fiber, then it's more expensive than glass fiber. So there is a lot of parameters into that. And
so I guess behind the question could be something like, well, what is the levelized cost of energy? And I guess the main driver for going to the very large turbines is that reduces the levelized cost of energy. So the cost per kilowatt hour in simple language reduces by the very big ones.
Yeah. Well,
12 megawatt machines should, all things equal, be much more efficient than 8 1.5 ones.
Yeah, well, of course, you say the market has shown that if it was more efficient to stay with smaller turbines, then the market would do that. So the race for larger and larger turbines continues, because that is more efficient. I'm not sure if you look at the single turbine, but you need to look at the total cost. So if you have more turbines, then you need more cables out to these turbines, and you need foundation for each turbine. So combined, it's more efficient to have a really big one. And right now we are at 13 megawatt, and well, that will certainly increase over the next coming years.
Okay, next question is from Peter Karapapos, and he says, with the blade size increasing and also installing blades on mountains, is icing on the blades a concern? If so, what would the basic requirements of anti-icing systems be?
And that's correct. And blades are installed in areas where you will see icing on the blades. In Sweden and in Canada and so on, we do have projects where you will need a de-icing system, and we actually have that. So we can we can provide that to customers that have projects in such areas and are in need of such systems.
Okay, so that's an add-on thing to
Yeah, yes.
Yeah,
it is.
Okay, there's a question from Mike Elkington, and he says, you said you see that the manufacturing processes remain at least partially manual.
Yeah.
Which aspects of manufacturing are most difficult to automate?
I think I'm not sure I can answer that. Can you read the question again?
Yeah, sure, I can do that. So Mike Elkington says that it's in your presentation you state that the manufacturing of the blades is still at least partially manual. There's a lot of manual labor involved, and so there must be an underlying reason for why it's difficult to automate to a further degree. So he asks, what aspects of the manufacturing process are most difficult to automate?
Yeah, but I say for us, it's not a question about how difficult it is. It's more a matter of what value it brings to us. So actually, there is a reason why the manufacturing process is still quite manual, and that's because it's the most cost-efficient way to manufacture, at least in the way we manufacture blades. And if you look at a worker, then he's quite a clever person, and you can use this person for different parts of the manufacturing process. If you have a specialized machine designed for a specific operation in the manufacturing, then it can only be used for that purpose. So it's the flexibility of, say, of a worker that brings advantage to us. And if you have expensive equipment, it actually needs to be in operation all time in order to bring a fair return of that investment. And that's actually also the reasons why we see that the manufacturing process are still quite manual. We do have machines, but it's mainly to overcome some challenges we have just because of the size and the fact that we need to have higher deposition rates. We simply need to lay down the glass faster than possible with manual workforce, as an example.
Okay, thank you very much. I think we have time for just one more question, and here's one coming on to. So you mentioned in your talk, John, that you were looking at additive manufacturing. Question is that do you plan to make parts with additive manufacturing? And I guess the answer is yes to that, but with thermoplastic. So maybe you can elaborate a little bit more about how you see additive manufacturing going into wind blade production.
Yeah, we certainly see some advantage in additive manufacturing, but certainly we also see challenges. So we are at the start of a learning path on that journey. We have produced, you can say, smaller parts of a blade with additive manufacturing. So we do have some experience, but there's still a long way to go before we will see that in our running production.
So thank you very much, John. I think we have to wrap it up now and have a little break before the next presentation. Thank you 1,000 times for a great presentation, and thank you also for the attendees for all the questions and for attending, of course. So Tim, can you put the